Okay, so this is lecture number 9. So this is called instant-based classifier, or what we call K nearest neighbor. For those who are doing final year project, you may have heard about this. Okay, so this is another classifier used for classification. So the basic idea of instant-based classifier is that they use distance in order to determine the class of membership for new unseen data. So this chapter will cover the key concept that define instant-based classifier and why they are considered lazy learner. And then we look at this method, how they use similarity to determine the class membership of a new unseen data. Okay, and we look specifically at a classifier called KNN. KNN stand for K nearest neighbor. So basically, what happened in the KNN is that they will find K nearest neighbor. K refer to number of nearest neighbor. So if we say K equal to 3, that means we are looking at, if K equal to 3, we are looking at the 3 nearest neighbor, and we look at the label for this 3 nearest neighbor, and we take the majority and assign that class label to the new unseen example. So this is a very simple classifier, but very powerful. Okay, it can be used to perform optical character recognition, facial recognition, because they are looking at the differences between the structure of the image. We can also use this to predict whether a person will enjoy a movie, and then we can use this one to identify patterns in genetic data. Due to the nature of this classifier, in which they use distant method to determine the class membership, so we can use this one for any type of dataset. So if a concept is difficult to define, so we can use this can to do the classification. Okay. So the foundation of instant-based learning, or KNN, they say if we have all the training example in our data set and also the class label. So this is the class label. Okay. So the nearest neighbor is defined as um, the nearest sample in our data set, and we will find the class membership and we assign to the new unseen data. So this is the X query. So meaning that we are looking at a new instant here, and then we are looking at the nearest training example that we have. Based on the class that we have, we will assign them to the new unseen data that we have. So this is for one nearest neighbor. We could also use K nearest neighbor, in which we will have more than one. So K nearest, it will take the K nearest neighbor, and we look at the majority of the label that we have here. Okay, and we will assign to the new unseen data that we have. So this is by looking at this one, we counting the number of classes that has the majority. That is for the categorical, but for this one, we are looking at the average. Okay. So the algorithm for KNN is that given K, or we need to choose K. So what happened is that the model will identify the K nearest record in the training data set, and then we will assign the majority label for the K nearest neighbor to the unlabeled test instance that we have. Okay. So for instance, if we have in our data set um, for this ingredient and we have the food type, this is the class. Okay. For each record that we have the details here, which is the sweetness and crunchiness. So if we plot them in a 2D, so we can group them based on the type. So this is vegetables, fruits, and also proteins. So if we have new data set here, a new instant, so what happened for the KNN, they will look at the nearest neighbor, the nearest sample. Okay, so it depends on K. So they will find the nearest K samples or instant in your data set. And based on this K nearest neighbor or K nearest sample, they will find the majority label for the K nearest neighbor and assign to this sample. I think if you on your mic, can you turn off them? Because yeah, okay. So the advantages of using KNN training is very fast. Basically, we didn't train them. We call it them lazy learner because we use distant method in order to determine the majority class level. So the model also can learn complex target function and did not lose any information. But the disadvantage of this is that slow at query time because if we have 1 million data, so we need to compute the distance between the new instant. This is the new instant to the 1 million data set that we have. And we also need a lot of storage because we need to store this. If you have outlier or irrelevant attributes, it will affect the performance because we depends on the distance, right? So if you have one column or one features or one attribute that has nothing to do with the class label, it will affect the accuracy. Okay. For the distance method, we can use the Euclidean distance or Manhattan, okay, or the L norm, but normally we use Euclidean distance, okay, where we n equal to 2 here, okay. So when n equal to 2, you have Euclidean. When n equal to 1, then you have Manhattan. Okay. In most cases, we will use Euclidean distance because we can uh, normalize the differences here, the negative sign here, and then make it smaller again. But before we can do this, we need to normalize our data using the range standard deviation. We could also, this is for numerical features. For the symbolic features, we can use the differences between the symbol. Okay. So for this one, we can use the value difference measure, VDM, in which we are looking at the probability of um, having that having that item to be in the class H. Okay, for example, this one, given the value for feature I, we will look at the probability of having class H. And this is another feature. So value for the um, different features, and we look at the probability of having class H. Okay. But in most cases, they use the Euclidean distance, for example, male and male. So the distance is 0. So male and female, the distance is 1. Okay. So we go back to the example that we have just now. So we have this data set. Okay. And we have new data set, new instance here. Okay. Suppose the tomato, we have sweetness 6, crunchiness 4. So if you want to measure the distance between this tomato to the rest of the data that we have, so we just take the Euclidean distance and then we measure. So this is the Euclidean, this formula that we have. Okay. So since we have 6 and 4, so we just minus this 6, like the square, plus 5 minus 7, no, 4, and then take the square, and then take the square root. So this is what we get. Okay. So based on the distance here, we are looking at the smallest one, nearest neighbor. So we say that, okay, the tomato, if k equal to 1, the nearest neighbor would be orange. So we take the fruit type here to assign to the tomato. Okay. But if we are looking at k equal to 3, so that means we are looking for the 3 nearest neighbor that we have. So we have 1, 2, and 3. So based on these 3, so we have fruits, protein, and fruits. So we take the majority label, and it turned out to be fruits also. So we assign this one to the tomato. So this is a very simple um, classifier, but before we can make it very efficient, we need to reduce the number of features, the number of column, because it involves calculation of distance. And also we need to normalize the value of our features. Okay? But the main issue that we have in KNN is that what is the best value for K. So we need to be careful. Okay, if we have Large K, large K, it will cause underfitting. So underfitting meaning that your model is um, performing poorly on the training, but perform well on the evaluation. So during the training, your accuracy is low, but then when you go for the actual one, you will have good um, good accuracy. So underfitting. Okay, during the training, poor performance, but during the testing, you have high accuracy. Okay, if you have smaller K, you will have overfitting. Okay, so overfitting is when you perform well on the training, but does not perform well on the testing. So during training, um, accuracy is high, but then during the testing, accuracy is low. So we need to balance what is the best value for K. So we need to test lah. So the term of rules saying that you take the square root of the number of sample that you have. So for example, if you have sample is 100, so the best K would be 10. Okay. So from here you can go up or you can go down. So this is another illustration. Okay, smaller K, a smaller value of K allow more complex decision um, boundaries. Okay. The problem is that we do not know whether the straight boundary or curved boundary better represent the true underlying. So this one is smaller K here. Okay, but if you have large K, so large K will you will have an overfitting, no no underfitting. So underfitting is when your model perform well during training but did not perform well during the testing. So underfitting. Okay. So this is what I mentioned just now. One-to-one practice is to begin K equal to square root of the number of training sample. So you start from there. Okay. So before we can perform the classification using KNN, because the method used for KNN is measuring the distance. So we do not want to have one feature to have higher influence due to the larger differences. So what we can do is that we can normalize the value that we have so that we have a range between 0 and 1. So in order to achieve this, we can use the min max or the Z score standardization. So this is depending on the mean and standard deviation. So this is for the min max. It will depends on the min max of that particular features or attribute. Okay. So like I mentioned just now, if we have okay, this is normally equidistant is used for numerical value, but if you have nominal data, for instance like this, male, so this one is looking at um, similarity. Okay, so that's why male uh, if we are comparing male and male, so this is one. But if we are looking at the differences, so male and male, it will be zero. So basically, differences equal to 1 minus similarity. Okay. So why do we call can an algorithm is lazy? Because we didn't do any modeling. Instead, we measure the distance between the unseen data to the k nearest sample that we have. Okay. So KNN algorithm has no abstraction occur, meaning that we didn't do any modeling. So they are also known as instant-based learning because we highly depends on the sample data that we have in our dataset. Okay? So they do not build any model, but instead they are looking at the distance. Okay. So like I mentioned just now, the KNN is highly depending on the number of features that we have. So we do not want to have so many features. So for that reason, we need to be able to filter which attribute, which features are the most important. So because the more attribute we have, we will have more calculation. So we do not want to have this. So for that reason, we need to do feature selection. So for feature selection, we have two methods. The first one is called filtering. So filtering. So this is just pre-select features individually using the info gain, or we can use the wrapper approach in which we will run learner with different combination of features, forward s- selection or backward elimination. So forward selection meaning that we, for example, if we have feature A, B, C, so we want to get the combination of features that we have. So we could choose A only or B only or both or B and C and so on. Okay, backward elimination, we have A, B, C, then we eliminate one of them to have A and B, or we eliminate A to have B only. Okay, so but we look at the first one first, filter approach. Okay, in the filter approach, basically we are filtering the irrelevant features that we have in our dataset. So basically we are using different function here to determine the importance of the features that we have. So this is your machine learning algorithm. So this is your filtering, in which we use different function to filter the importance of the attribute that we have. Once we have selected the best feature here, then we feed into our modeling. So we call it filtering because we filter before we put them in the machine learning model. So we can use info gain or entropy to filter them. So if we compare with the wrapper, so the wrapper here, so when we select the best feature subset here, we are using the same model here with the modeling that we have here. Okay, so meaning that we select the feature based on the performance of this machine learning here. So if we just pick feature A, and it will increase the accuracy of the machine learning here, then we will choose A only. So we are selecting the features based on the performance of the machine learning algorithm here, which is actually the same with here. So once we have the best feature set subset here, then we feed into the machine learning here. So if we have A, B, and C, so we have a choice of having A atau B or C or AB or AC or BC or AB and C. Okay. So so we will test the performance of this machine learning. What if I only have A only or B or C or both A and B and so on? So we will take the combination of features that will have the highest accuracy for this machine learning here. So we take the best combination of features or best feature subset to be fed here. Okay, and this is where you perform um, the testing tu lah. Okay, so wrapper, it is called wrapper because the whole thing is using one machine learning algorithm. The same, they are using the same. So that's why they call it wrapper. We could also use feature weighting to show the importance of the features. So we can use binary. For example, if we have A, B, C, so if you have binary 101, that means we will eliminate B. Okay? We don't use B. We could also use another kind of weightage. If we have A, B, C, so we can say this is 0.8, this is 0.1, 0.1. So that means A is more important compared to B and C. So that is what we call features weighting. Okay, let's have a look at how do we apply this one in the practical. So in this example, we have the Wisconsin breast cancer diagnostic dataset. So we have 32 features, 32 column, and we have 569 sample. Okay. So if we have one sample, one unseen sample, so we need to compare with all of these sample data that we have. Okay. So we have one feature, which is the ID, and we have the class label, which is the cancer diagnosis. And the other one is the lab measurement, the 30 features that we have. Okay. So let me switch to the other software. Okay, so I will point my send working directory to here. So the first thing that we will do will import this one. So basically what happened here is that I will import from this data set and I will say all the string of character to be character and not a label. Okay. So if I look at the structure of my data set here, so we have the label here diagnosis as character. Okay. And the ID is the ID. Okay. So what happened if I import this one using this is true? So that means all the string of character will be changed to label. So over here, you look at the diagnosis here, so vector. Okay. So let's set this one to false, and then later on we will change the label. Okay. So what happened here is that we do not want to include the ID because this is irrelevant features. So we will remove the first column here. Okay. And then if we look at the structure again, so have we have eliminated this ID. Okay. So this is just we are saying that okay, we will reduce the no, we will throw away the first column, but I will update my data set again. Okay. And we look at the label that we have for the this column. So this one will tell you the number of instant for each of the character that we have, B and M. Okay. And we look at the label here. All of them are in character, string of character. So we want to change this one to a label. So this is how we change them. So basically we are taking this value, string of character, and we change them to become a vector. So we have this benign and malignant. So for all the B will be changed to benign, all the M will be changed to malignant. Okay? So if we look at the value for this one, so we have updated them to be the label. Okay. We can also look at the percentage, the proportion of data that we have. So we are looking at the diagnosis here. So we are looking at the proportion here. So this one will give you the percentage of number of instance for each class that we have. And we look at the value for two of the no, three of them. So we look at radius mean, area mean. So if we look at the value here, the radius mean has 28 maximum. But if you look at the smoothness mean, the maximum one is 0.16. So there is a huge differences between these two columns. So of course the radius mean will have higher influence on the differences between two instance in your data set. So we don't want to have this effect of having higher influence on the radius mean, so we need to normalize them so that all our features will have the range between 0 and 1. Okay, so we will use the min max function. So we will define a function called normalize. So we will use the formula that we have, which is the um, we take the value x minus the mean of that particular features divide by the maximum of that particular features minus the mean. Okay? So if we um, testing using this value, for example, we want to have normalized value for this, so we will have this. So similar thing if we do different range, so still we will have the after normalization we will have 0 and 1. Okay? So we will apply this one to all the column that we have. Okay? So in this case, I will apply for the list of all the column that I have for this function, and I put in the data frame or table. So now if I look at the summary, yeah, so the summary for this mean is 0 to 1 only. So if we repeat this one again, so you can see that the range of value for radius mean, area mean, smoothness mean is between 0 and 1. Okay, so this is okay. We can perform the can-end now. Okay. Um, although we don't have any training and tests for this one, but we just have a look here. So we have the training data set and testing. Okay. So we divide into two. One is training data set and one is for the testing data set. And also we have the label. We extract the label from our data set here. So one is for the training and one is for the testing. So what happened here is that, okay, I'm taking column 1 up to 469 and I'm focused on column 1, which is the diagnosis label. So this is I'm extracting the label for the training. I'm extracting the label for the testing. Okay. So we will upload this class in the memory. So this is for the NN. Okay. So what happened here is that I'm using the CanN and I give this training dataset, and this is the training dataset. So which means that for each of the sample that I have here, I will find the 21 nearest neighbor here from the training. Then I will decide the label for this test dataset that I have. Okay. So what you have here will be the label for your test dataset here. So we want to compare this with the label of the test dataset that we have. This is the predicted label for your test dataset here. Okay. We could also use k equal to 10, so we just compare. So this is for the second result here. So for the second model here, where k equal to 10, so this is what we get. So we can compare the performance between these two. One is K21, one is K10. Okay, so we can draw the confusion matrix. Um, so this one we will draw for the first one. So we are comparing the actual label with the predicted label that we have using the cross table. So in this case, we have two error only, two sample misclassified. Okay, so this is the confusion matrix. So this is for k equal to 21. If we repeat again for k equal to 10, so in this example, we have 4. Okay, so that means k equal to 21 give you higher accuracy compared to k equal to 4. No, k equal to 10. So this is K10, this is K21. K21, only two sample, which is the label is malignant but pre- predicted as benign. But for this one is 4. Okay, so this is how we use scan to perform the um, prediction. Okay, so any question? If you okay, can you type number 2?